legend has it that the name Babi el Mandeb, meaning Gate of Tears or Gate of Grief, refers to the tragic loss of life during an earthquake that split the Arabian Peninsula from the Horn of Africa. This name also alludes to the treacherous navigation challenges posed by the waters in the region. Here lies a region where three tectonic plates are diverging to form one of the Earth's most dynamic and fascinating landscapes. The smaller Arabian and larger African plate are pulling apart, creating the expansive rift known as the Red Sea. Simultaneously, the Indian plate is also drifting away from the African plate, giving birth to the East African Rift Valley, an enormous geological fault that could one day split the Horn of Africa, potentially forming a new ocean. This rift extends from the Red Sea into Eritrea, Ethiopia, Kenya, and beyond, making the vast East African Rift System. This divergent tectonic activity has shaped the remarkable Afar Triangle, region of volcanic lowlands, salt lakes, and magma-ridden landscapes. Known for its extreme geological instability, the area experiences frequent earthquakes and volcanic eruptions. It is also one of the hottest and driest regions on Earth, with temperatures soaring year-round. Among its dramatic features are some of the world's lowest points, situated more than 100 meters or 330 feet below sea level. Beyond these lowlands, towering mountain ranges, such as the highlands of Eritrea and Ethiopia and Mount Kilimanjaro, rise along the tectonic boundaries, showcasing the striking contrast in this geological theater. Significantly, this region holds vast untapped geothermal energy resources. With Eritrea at the forefront of the rift's expansion, this video will focus on Eritrea to explore how this unique geological feature is shaping the area and examine the potential of geothermal energy to transform the country's energy landscape and that of the broader region. Join us as we examine the risks associated with the seismic activity in the region, as well as the opportunities to harness geothermal power, a renewable energy source driven by the same tectonic movements that shape this inspiring landscape. Eritrea is situated on the African side of the Bab el-Mandeb Strait, a key waterway that connects the Indian Ocean to the Mediterranean Sea via the Red Sea and the Suez Canal. This strait is critical for the movement of petroleum and natural gas exports from the Persian Gulf to Europe, making it a strategically important region for global powers. Later, we will explore how Eritrea's strategic geopolitical location has posed challenges to its development as a nation. For now, let's focus on Eritrea as a convergence point of tectonic plates, extending from the sea into the African continent, and as a place where extensive geothermal energy research has taken place since the early 1900s. Before delving into the details of the research, it's important to first understand the basic concepts of geothermal energy and geothermal power. The word geothermal comes from the Greek words geo, meaning earth, and thermal, meaning heat, referring to the heat stored within the earth. This energy is found in reservoirs of hot water and steam located deep beneath the Earth's surface. The source of this energy lies in the Earth's interior, which is made up of four main layers composed primarily of iron, nickel, and silicate materials. The deepest layer is the inner core, which is solid and made of iron and nickel. Temperatures here are believed to reach up to 10,000 degrees Fahrenheit, which is comparable to the surface temperature of the Sun. Despite these extreme temperatures, the immense pressure prevents the iron and nickel mixture from melting, keeping it solid. Surrounding the inner core is the outer core, a molten layer of iron and nickel known as magma. This layer remains liquid due to the high temperatures and lower pressure compared to the inner core. Above the outer core is the mantle, the thickest layer of the Earth, composed of both magma and solid rock. Temperatures within the mantle range from 300 degrees Fahrenheit in the upper mantle to over 7,000 degrees Fahrenheit in the lower mantle. The upper mantle is mostly solid silicate rock due to lower temperatures and pressures, while the lower mantle is molten because of the higher temperatures. The lava we see on the Earth's surface comes from the lower mantle, where it rises through fractures and faults. Finally, the crust is the Earth's outermost layer, composed of solid rock that forms the continents and ocean floors. The relatively cooler temperatures at this layer keep this layer solid. The crust is broken into many fractures and faults called tectonic plates. According to scientists, these plates shift about an inch or a few centimeters each year in a process called continental drift. Since all seismic activity around the world occurs along or near tectonic plates, understanding the science of tectonic plates and continental drift is crucial for both disaster preparedness and resource exploration. There are 7 major tectonic plates, as well as many smaller ones, which can be categorized into 3 types: convergent, transform, and divergent. Convergent boundaries occur when 2 plates collide, often forming mountain ranges. For example, the Himalayas were formed by the collision of the Indian plate with the Eurasian plate, while the subduction of the Nazca plate beneath South America created the Andes, the longest mountain range in the world. Transform boundaries happen when 2 plates slide past each other horizontally, generating friction and causing earthquakes. The San Andreas Fault in California is a well-known example of this type of boundary, where the Pacific plate and the North American plate slide in opposite directions. Lastly, divergent boundaries form when 2 plates pull apart, creating rifts. The Red Sea, formed by the separation of the African and Arabian plates, and the East African Rift System, which is the result of the African and Indian plates drifting apart, are both examples of divergent boundaries. Understanding these fundamental geological processes is key to grasping how geothermal energy is generated and why regions like Eritrea, situated along tectonic rifts, hold great potential for geothermal power. Geothermal power, which harnesses the Earth's heat to generate electricity, relies on groundwater or rainwater that seeps deep into the fractured crust. As this water is heated by hot rocks, it forms large reservoirs of steam and hot water. Some of this mixture rises naturally to the surface through cracks in the Earth's crust, creating geysers and hot springs. In certain cases, the rising water interacts with surrounding rocks, altering its chemical composition and forming vibrant acid lakes, such as those found in the Danakil region. However, much of the hot water and steam remains trapped in underground reservoirs, serving as the primary source of geothermal energy. To generate power, the steam and hot water from these reservoirs are harnessed using various technologies. The most natural and cost-effective method is the dry steam power plant, which extracts steam directly from high-temperature underground reservoirs. Steam is collected from multiple wells through insulated pipes and directed to a central facility, where it powers a turbine connected to a generator. After the steam condenses, it is cooled and re-injected back into the reservoir, where it is reheated, allowing the cycle to continue. This method represents the simplest form of geothermal power generation. However, since steam reservoirs occur mainly in regions along tectonic plate boundaries, areas like Eritrea, California, and Iceland are particularly well suited to this technology. In regions with slightly lower reservoir temperatures, where the resource is a mixture of steam and hot water, flash steam power plants are used. These plants operate by extracting hot water or a combination of water and steam. The steam is routed directly to the turbine for electricity production, while the hot water is pumped under high pressure into a surface tank, where the pressure is reduced, causing the water to vaporize rapidly or flash. The resulting vapor drives the turbine, and any remaining liquid can be flashed again in a second tank to produce additional steam. This process, known as a double flash power plant, can yield 15 to 25% more steam, increasing energy production. Finally, a more recent technology, known as a binary cycle power plant, is designed to extract power from lower temperature water. In these plants, heat from the hot water is transferred through a heat exchanger to vaporize an organic fluid with a much lower boiling point. The vaporized fluid is then used to drive a turbine. This method allows for power generation from wells with water temperatures as low as 170 degrees Fahrenheit or 76 degrees Celsius. Additionally, because low-temperature water is used, artificial geothermal reservoirs can be created by injecting water into shallow wells to be heated and pumped back out. In addition to advancements in power plant technology, innovations in geothermal energy extraction, such as enhanced geothermal systems or EGS, are gaining momentum. EGS involves drilling 2 wells into deep crystalline rocks and connecting them through a network of fractures. A pressurized fluid, typically water, is circulated through these fractures, creating an artificial geothermal reservoir. This technique allows for the extraction of geothermal energy from areas where natural reservoirs do not exist, expanding the potential for geothermal power generation. Now that we have a basic understanding of geothermal energy and how it's harnessed for power, it's clear why regions along the edges of tectonic plates are home to some of the world's most promising untapped geothermal energy resources. For example, the San Andreas Fault, which stretches over 800 miles and extends 10 miles deep into the Earth, has enabled California to develop the world's largest geothermal power plant, the Geysers Geothermal Complex. This facility generates between 700 megawatts and 900 megawatts of electricity, enough to power nearly 1 million homes. Similarly, Iceland, located on a divergent plate boundary, taps into the geothermal energy beneath its surface to supply over 90% of its energy needs. On the other side of the world, the Danakil region and the East African Rift System, where 3 tectonic plates are diverging, present a vast geothermal potential. A 1996 study by a joint Eritrean government and U.S. Geological Survey team identified the Alad Dome in Eritrea's Danakil region as a key site for geothermal energy production. The Alad Volcanic Center, a 700-meter-high mountain spanning nearly 7 square kilometers, is located 120 kilometers south of Massawa, Eritrea's main port on the Red Sea. This volcanic area lies at the heart of the active Danakil Depression, an active crustal spreading center, making it a prime candidate for geothermal energy. The study identifies several geothermal sites within a 10 square kilometers area of the Alad Dome, with reservoir temperatures ranging from 190 to 350 degrees Celsius at shallow depths, suggesting a significant electrical-grade geothermal resource. The relatively shallow reservoirs offer lower drilling costs, and the high temperatures make it feasible to generate power using all 3 types of geothermal power plants. In addition, the presence of recent volcanic activity in the area indicates ongoing crustal spreading, which suggests the resource's long-term sustainability. The next steps involve deep exploration drilling to gather data on subsurface conditions and designing infrastructure for power generation. Unfortunately, the project faced delays due to the challenges Eritrea has experienced in recent decades, particularly regional instability. As mentioned in the introduction, Eritrea's strategic location along a vital global trade route has historically attracted the attention of foreign powers, including the Ottomans, Europeans, and the Americans, leading to centuries of conflicts and instability for the Eritrean people. After years of war for independence and subsequent conflicts to preserve it, Eritrea has finally achieved a degree of stability. This newfound peace now opens the door for economic development. Recognizing energy as a key driver of economic growth, Eritrea is prioritizing the development of its energy sector. With its favorable geology, the country is well positioned to harness its vast geothermal potential. Tapping into this resource could transform the economy and enhance energy independence. Geothermal power offers a clean, sustainable energy source for homes, industries, and transportation, reducing reliance on imported fossil fuels, while creating jobs and spurring economic growth. As Eritrea continues to explore its resources and develop its economy, it holds the promise of becoming a regional hub for clean energy. The shallow geothermal reservoirs coupled with a stable political climate make Eritrea a true geothermal goldmine. Thank you for watching. Be sure to check out our other videos on geothermal energy and renewable resources to learn more about how these technologies are shaping the future of sustainable energy.